Okay, so here's what we've got today. We're going to discuss what Gavin described as easy homework. Make sure everybody hasn't made any dumb mistakes on that one. And then we're going to get into what's called angular momentum. It's similar to linear momentum, but completely different. So let me give you some hints about some of your answers. So that answer on number 5, like what's the linear velocity of someone standing on the equator of the Earth as they go around, that should be in the mid 400 meters per second. Okay, it's a big number.
What were we talking about?
Number 5.
Oh,
So, but that actually created a problem once they began. It's like, okay, hey, does the Earth stationary? Does the Earth spin? And then that led into this whole idea of like, well, if we're going that fast, why don't we feel it? Because like the speed of sound is about 340 meters per second. This is like 120 meters per second faster than the speed of sound.
that's pretty fast.
It's pretty fast. And the argument was like, well, then why do we even have oceans? Why hasn't all the water spun off the Earth? Okay, because if we're going that fast, why hasn't things just flown off? But then if you look at then the other side of that is if you look at, why did you do that? Hold on. Oh, it's going to be one of those days. So one of the calculations, and you did this back when we were doing centripetal motion. So if you look at the gravitational force of like a 70 kilogram person standing on the Earth as it spins, the centripetal force that you need to hold like a 70 kilogram person on is only about 3 newtons, okay? That's all you need in terms of just to keep them moving in a circle. Well, if you take 70 times your gravitational acceleration of about 10 meters per second squared, you get about 700 newtons. So the gravitational force is about 700 newtons. You only need about 3 newtons of that to keep the person from flying off. So that's how we can still have water and things like that.
So if a person didn't have that, they would just like fall off the Earth?
Or you'd go flying off. So just like me swinging the circle around like a rubber stopper, when I let go of it, it goes off in a straight line. The same thing would happen at the Earth. If we lost gravity, all of us would turn into straight line projectile motions. It would be bad.
That would be scary. Wait, would I fly into the wall?
What if I just like held onto the table?
You couldn't, not at that speed. Okay, on number 6. Keep in mind you want the answer from the distance from Joe, okay? And here's an easy way that you can check to see if your answer is right. So you're saying, here's George, here's Joe. Whatever you think that distance is to Joe, take whatever you think that distance is, whatever that radius is, multiply it by the mass of Joe times g, and then see if you have the leftover distance to George multiplied by his mass by g, and see if those two numbers are the same. If they are, odds are you did it right. If they're not, it's a train wreck, okay?
Muhammad Ali.
So, there's that. Your answers to problems 7, 8, and 9, every one of those answers should start with a 1. Okay? Vastly different orders of magnitude, but every one of them should start with a 1. Okay? If number 10, if that time is wrong, probably everything is going to go wrong. So if you look at what you all are used to equations, like v squared equals v naught squared plus 2ax, the same mathematical relationships exist with angular motion. You could have omega squared equals omega naught squared plus 2 alpha theta. Where you have V equals V naught plus AT, you can write that as omega equals omega naught plus alpha T. Okay? They're all the same. They are all the same. Now, what you're going to see today, the one equation that you cannot use to cross over between linear and angular motion is F equals ma. That is the one equation you are forbidden from crossing over. Okay? We'll talk about why you can't do that. So if something's spinning, I'm just going to begin to plant this seed now because you're going to hear me say this again and again and again. You cannot use F equals ma on something that spins. Okay? Can't do it. So on number 10, if that time is wrong, kind of everything else is probably going to be wrong. Your time on number 10, this is an ish, but it should be around like 5 seconds. Okay? So 10A should be around 5 seconds. On number 11, that angular acceleration in radians per second squared should be something around the legal drinking age. You okay, Louise?
Yeah, I just got like,
I just look up and you're like, oh!
I got like a
Like someone shot you in the arm.
I got like a pain in my collarbone.
I hate
Did you
that.
say what's he about the legal drinking?
Like how
On
close?
number 11.
Oh, well, yeah, I should read it down.
Yeah. No. The answer to 10A is around 5.
Yeah,
Do
and
you,
then
do you have
Your
power?
answer to number 11 is around the legal drinking age.
What'd you
So it's
get?
what?
Okay?
Uh,
Are we good?
I mean, I'm confused why I did it wrong, but
On which one?
didn't he tell us
10 and 11,
Yeah, he told us that one.
Well, on 10, you're going to start with theta equals 1/2
that's what I did.
plus omega naught time, right?
Yeah,
You don't have to worry about that part because that's 0.
no,
Okay?
yeah,
Did you convert the revolutions into radians
yes,
Which one?
on 10A? And so then it's just 2 theta over alpha, and the square root of that's going to get you time.
yeah, that's what I did.
What are your numbers that
What do you have for theta?
18.8,
What? Free.
Whoa.
I got 75.
For which one?
There's 12 revolutions, right? 1 revolution is 2 pi radians.
yeah, I don't know where I got that.
12 times
Wait,
20.
so is it times 2 pi?
Yes.
Yeah.
It depends on the
Did you
situation.
just-
That makes
No,
sense.
no.
I divided by 2 pi.
Well, no, if you're going the other way.
So we have in this situation.
So if it's radians for revolutions, you divide by 2 pi?
Yeah, so if
I
you
mean, yeah, that
had,
makes sense.
I thought it was
like for
stupid.
example, on number 8, you're going to find the number of radians, but it asks you revolutions. So if you know the number of radians, like let's say it moves through 48 radians, okay, which is tough. It's like what's 48 radians? I don't know. So then if you divide by 2 pi to get it into revolutions, that's something more visual. Oh, okay, great. I can count how many revolutions. I can sit here and count how many times it goes around. It's tough for me to sit there and count radians, but I can count revolutions.
Oh, I thought I was making a big booth doing that. Yeah.
No. But again, here's what you have to be careful, is that when you divide by 2 pi, you just can't put 48 divided by 2 pi, okay?
Put it in
Those
for
divide the
parentheses.
48,
Yeah, because
so
they're going to divide by 2, and you're going to get 24, and then you're going to multiply it by pi,
Yeah.
which is going to get you a completely jacked up answer.
Yeah, I figured that out last night.
Again, I
You
should have
said that
told you that
yesterday.
yesterday. That
Yeah,
was
no,
on me.
but I forgot you said that, so I
No,
just
I
kinda
figured
did
that
it,
out
got
on the
really
math
covered,
test
and made
because
it
I got
sense.
like every single one wrong.
That's also all about the order of operations. Okay, we're good. Going once, going twice. Okay, then did you get that figured out?
I hopefully will.
Okay, hopefully so. All right, so here's today's lesson. Get that handed in, by the way.
Oh wait, I need help on one of them in the textbook.
Which one?
I was confused on number 5.
Hold on. So, here's the hinge, right?
Yeah.
Okay? And so, imagine that here's force A. There's B, C, D, boom, whatever that last one was, E.
Alright.
Okay? So imagine here's the door. If you pull on the door, how much torque are you gonna generate?
A lot.
No,
Not.
none.
Yeah.
You're not gonna make it spin by
Do you
pulling,
think someone could pull a door off?
no, just,
I thought you didn't generate torque. I thought you did that with force.
you do. But if the force is just in the direction of the door,
Mm-hmm.
that's not gonna make it spin,
Yeah.
okay?
Okay.
So it's only the component of that force that's at right angles to the door that's gonna make it spin.
Yeah.
So this one is gonna pull the door in this direction, which is gonna be,
Positive.
yeah, well, counterclockwise.
Yeah.
Yeah. This one is gonna make it spin clockwise, but this torque out here will be bigger than this torque because of the fact that
Radius
it's
is
further
bigger.
out.
Okay. That
Do we
makes
have to
sense.
say that?
No,
It just, okay.
I'm just pointing that out.
Okay.
I just put like plus minus plus.
Yeah,
minus.
that's all you have to do, is just plus minus, that's it.
And then for E, we just put neither.
Huh?
For,
It says zero.
Yeah.
You're supposed to put zero.
Yeah, there's just,
I put
That's it.
neither.
okay, so today we're gonna talk about the concept known as moment of inertia and angular momentum. So if I ever get the chance to retire, I keep getting threatened if I do,
By who?
this would be, any number of people.
Actually?
Former students who want me to teach their kids and administration. It's like, no, you can't retire. So,
We just that good.
well, anyway,
No.
but if I did retire and I could come back and give one lesson, this would be the lesson I would give. Okay,
Well,
this
that
would be
means
the
I'm
one.
not gonna like it.
Because a whole bunch of random things will kind of make sense at the end. So, let's talk first about moment of inertia. So this is like the cousin of inertia, okay? But it's different. So if you look at inertia, what's the only thing that determines the amount of inertia an object has?
It's mass.
Mass, that's it. The amount of stuff, that's it, okay? That's it. It is only the amount of stuff. If it's moving, spinning, at rest, on the moon, doesn't matter. Inertia is only determined by stuff, okay? And the resistance to change in its velocity. That's it. Now, moment of inertia, though, is relating to things that are going to spin around an axis. So, moment of inertia is the resistance to undergo a change in omega. Okay? How easy it is to get it to speed up. But if it's spinning, how hard is it to get it to slow down? Okay? But it's the same idea of inertia. If something has a big moment of inertia, it's really difficult to get it to spin. But once you get it spinning, it's really difficult to get it to stop. So if our Earth, for example, our rock, has a huge moment of inertia, and that's okay. Okay? We want that to happen. This is why an hour is consistently 24 hours. Okay? Excuse me, one day is 24 hours. It isn't like, we get a heavy snow on the North American continent. That slows down the Earth because now it has more mass on it. Great, now an hour or a day is 23 hours and 58 minutes. It melts. Now we're back to 24 hours again. It gets hit, we get hit by a small asteroid. That's going to slow the Earth down or speed it up. And we're continuously changing the length of the day. No. Earth is massive, okay? Has it slowing down over the years? Like, if you look at a long geological scale, yes, the Earth has slowed down. but it's a very, 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 very slow process. So here's one difference between moment of inertia and inertia. Inertia itself does not have an equation to calculate inertia, okay? It's just, hey, here's an apple, here's the styrofoam apple, here's a 1 kilogram mass. 1 kilogram mass is going to have more inertia than the styrofoam apple. Okay, that's it. Okay, there's nothing to calculate. It's just, you just look at mass. Moment of inertia, though, is a formula. So there's two things that impact moment of inertia. One is mass, and the other one is where the mass is located. Where the mass is. So, if you look on the lecture notes that I gave you all yesterday, and there's also a bigger list in your book, okay? There's a whole list of moment of inertias in your book. Moment of inertia has to be calculated. So, here's like the mother of all moment of inertia equations. Moment of inertia is represented by the letter I. And the one idea where all moment of inertia equations come from is that it's mr squared, okay? So, you'll see that this does not work for every moment of inertia. So if you look on that sheet, is it a hollow cylinder? Is it a solid cylinder? Is it a hollow sphere? Is it a solid sphere? Is it a door? Whatever it is. So, one thing I want you to understand, we're going to talk about mr squared, but listen to me. You can only use mr squared under two circumstances. If you are specifically told it's a thin hoop, okay? Literally, it will tell you, this is a thin hoop, okay? That's how you know to use mr squared. The other thing is if it's a point mass. So, the classic example of a point mass would be I take this rubber stopper and I swing it around over my head like this. So this would be the mass of the stopper, this would be the radius. What makes a bigger difference in terms of moment of inertia? Changes in, what is wrong with you?
Oh, I thought you were talking to Gavin.
No. Oh, I hate technology. No, it's not a good morning. Go away. I don't even see an X to make this thing stop.
There it
Okay. So, no. Stop. Okay. So what's going to make more change? A change to mass or a change to radius?
Radius.
Radius, why?
It's squared.
Because it's squared. So a point mass would be a rubber stopper going around over my head.
Yeah.
If I increase the radius, I've increased the moment of inertia. Okay? Now, here's what's different. Inertia, mass. That's all you have to worry about. Moment of inertia, you have to worry about two things. How much mass there is and where the mass is located. Okay? So there's two things. Now, if you look at the units, you have mass measured in kilograms and you have radius measured in squared. Okay? So there's no cute way to do this. Okay? Moment of inertia is just kilograms meters squared. So if you look at all those different formulas, they all have something in common. They all end up in kilograms meters squared. Some might be like an R1 squared plus an R2 squared times mass. There might be a 1/12. There might be all these weird fractions. But at the end of the day, all moment of inertia equations end up at kilograms meters squared. Okay? So, because of that, I could have two different objects that don't have the same mass, but they could have the same moment of inertia. So like I could take this rubber stopper and swing it around over my head, and that would have a certain moment of inertia. I could take a bigger object that has more mass and have a smaller radius and have it have the same moment of inertia as the rubber stopper does. So it's kind of like momentum. Because it's dependent upon two things, I could have a large mass moving with a small radius, which could equal a smaller mass moving with a larger radius. So I can have two objects with unequal mass have the same moment of inertia. But I cannot have two objects with unequal mass have the same inertia, because inertia only depends on mass, but moment of inertia depends upon mass and radius. Now, keep in mind, moment of inertia is a measure of resistance to undergo angular acceleration. So, with that said, I've got this aluminum stick with brass weights on it. I'm going to try and balance it. Okay, there's two ways that I can try and balance it. I can try and balance it with the mass at the bottom, or I could try and balance it with the mass at the top. Okay? In both situations, what's the same?
The mass.
Mass. What's the only difference? Where it's located, right? It's the only difference. So, what's going to be easier to balance? With the weights at the bottom, or with the mass at the top?
One at the bottom,
Louise says bottom. Why?
because if it's at the top, it'll kind of like want to like, if it's like leading one way, it's gonna want to go that way. You know what I
Okay.
mean? But when it's at the bottom, it'll try to, you know, I don't know how to explain it. Well,
Gavin?
Bottom,
Bottom, why?
so the radius is smaller, so the I moment of inertia will be smaller.
Okay, that's true.
So
So how many vote bottom? 1, 2,
It'll
3.
just be easier to recover because the moment of inertia is there.
So it'll be easier to recover.
So you
Okay.
can sit there.
Elliot?
My logic is saying bottom, cause I feel that, but I feel like you would want,
I don't know, I feel like as a
Higher
kid, when you balance
resistance?
something, you always
Yeah,
have
if you
the top.
balance like a bat, like the bigger part's always at the top.
What?
if you would want a higher one so that it's not changing as much, cause higher resistance to change momentum would be not moving.
Let's talk about this. If I were to try and balance this, what do I want the angular velocity of the end of the rod to equal?
Zero.
0. I do not want this thing moving, right?
Mm.
I do not want it to undergo angular acceleration. I want it to remain at rest. Okay? So, Gavin, let's talk about what you said. Down here, I've got MR squared. Is I big or small?
Smell
Small. Here I've got a big I, right? Okay? So if I try and balance this right here, okay, put it in the palm of my hand. I'm going to try and balance it. Okay? All right, I can balance it, but it's kind of tough. Now I'm going to do this. Hold on. Okay? Exponentially easier that way. But here's the deal. Having this up here at the top has a big moment of inertia. So it doesn't want to move. It wants to remain at rest. But once I get it moving though,
It's harder to.
it's harder to stop. Okay? If I go like this, I can move this back and forth very easily because there isn't much mass up here to move, okay, to start and stop. If I go like this, okay, then it's you can feel this, like it's difficult to get it to move. But once it is moving, then it's tough to get it to stop. Okay? So, here's what I want you to get. Mass is towards the outside, big moment of inertia. Mass is towards the inside, smaller moment of inertia. Got that idea? Okay. Caitlin, stop the camera and bring it to the back of the room.